Okay, so let's have a look at one of the questions from the homework. This is exercise 12B, question 16, and it says a triangle, in particular, a scalene triangle, has coordinates 2, 0, 0, 5, 0, 0, and 4, 2, 3. Work out the area. Now there are some ways that there are probably some shortcuts here because of the fact that these coordinates look like this. They've got something where they've only got an x coordinate, but I'm going to actually teach you this question in a more general kind of way that will help you do this for any kind of thing. Further mathematicians, you probably wouldn't use this technique. You would do the angle between two vectors using the dot product. But for everyone else, you would draw a triangle like this. Doesn't matter if it's to scale or not. We've got A, B, and C. Let's call this one A, let's call this one B, and let's call this one C. As vectors, then I've got 2, 0, 0, 5, 0, 0, and 4, 2, 3. And all you're going to do here is you are going to find out the length of each side of the triangle to come up with something that just looks like this. If you imagine knowing the length of a triangle like this, tell me something you could possibly do to this triangle. Rayhan.
I think it's cosine rule.
Good. We could do the cosine rule, and we could find out an angle over here. So first of all, we could use the cosine rule. Anyone remind me what the cosine rule is? A squared equals b squared? Yep. Okay, so we could do that to find out what A is, and then after you've used the cosine rule, what could you then do? Good, you could then just do the area triangle rule, and you could just do a half AB sine C. However, it wouldn't be a half AB sine C, it would be a half CB sine A. Okay? So if you ever have a question where they just give you the 3 coordinates of a triangle, there are 2 things that you need to do. First of all, you need to do the cosine rule to find out the angle that you have. Then, once you know what that angle is, you also know what those 2 sides are because you've worked out the side lengths of them. You can then do half AB sine C, but the rearranged version of it, to find out what the area is. I'm not actually going to do that because I just think it's quite like time heavy and stuff. Okay, that will work for any any triangle at all. You could think about these coordinates in a different way, but actually it's going to just be extra work. It's easier to do it like this. Okay. Any other ones from the homework? Okay, so what we're going to do then is we're going to be doing stuff that feels like we're recapping year 12, which we are sort of recapping year 12, but we're just going a little bit deeper now. So some geometric problems that we've got here. It says A, B, C, and D are the points. Let's just label them A, B, C, and D, respectively. Find A, B, and DC, giving your answers in the form PI plus QJ plus RK. Show that the lines AB and DC are parallel and that DC equals 2AB, hence describe the quadrilateral ABCD. We actually could answer the last part of the question straight away. Anyone think they could answer the last part of the question straight away? I'm going to give you 30 seconds to think about it. Do you think, given this sentence they've given you here, do you think anyone could have a go at trying to describe that? Have a little think about that for 20 seconds and see if anyone's got an idea. You can talk to each other if you want to. Oh, okay, right. Anyone think they can describe the quadrilateral ABCD? Is it an isosceles? No, it's not. No, it's not a rectangle, actually. It's a trapezium. So actually, the answer is a trapezium. We're going to see why it's a trapezium in a second. But it's interesting, you don't actually need to even do the question to know that it's a trapezium here. So very quickly, let's just do part A of the question. Okay, Masuma, if I've got the vector AB, what do I do to find the vector AB? Which way round do I subtract them? This should be good. Did someone whisper that to you, or did it just come to you very, very last minute? Yeah, it's always the second letter take away the first letter, okay? It's just the shortcut way of remembering that. So it's going to be 1 minus 7 minus 3, take away 2 minus 5 minus 8. which gives us, this is where I can always make easy mistakes, 1 minus 2 is minus 1, minus 7 minus minus 5, minus 3 minus minus 8. Okay, good. We're then also going to work out the vector DC.
Should we put in over here?
Yeah, we should actually. So we're going to say that that's minus I minus 2j plus 5k. DC, let's do that one up here. So that's 2, 19 minus 20 minus 0, 15 minus 10. Got a bit more space. So that's 2, 4. And I did the wrong way, yes. So actually, it shouldn't be that, take away that. It should be C, take away D. Thank you for pulling me on that now. So C minus D, 0, 15 minus 10 minus 2, 19 minus 20. It should be a 2. And that's minus 2 minus 4, 10. Which is good, because we're about to see the thing that it's asking for us to do. So that's minus 2i minus 4j plus 10k. Okay, so we've done that first bit. It then says show that the lines AB and DC are parallel. That was our part A of the question. Let's just box this off so we've got a bit more space. We're trying to show that DC equals 2AB. We can't really start with that sentence, so instead let's start off that DC is equal to 2 lots of minus 1, minus 2, minus 5, which is minus 2, minus 4, 10. That shouldn't be minus 5, should it? It should be 5. Which is equal to 2AB. So they're parallel to each other, and in particular we can see something more, that DC is, what else can we tell? Same direction, that's parallel. What else can we tell about DC? What does this tell me about DC? Tell me something more about DC. Yeah, come on. What does the 2 tell us? It's double the length. It's not just longer. It happens to be precisely double the length of AB as well. So for part C of the question, we already know that the answer is it's a trapezium, but you know the letters A, B, C, D, they follow around the outside of the trapezium, of the quadrilateral. So you've got DC and AB. Well, let's just do any sketch. If it's just A, B, C, D, that's roughly what the quadrilateral is going to be in that kind of formation. The sides that are parallel is the top bit and the bottom bit. And we know that the bottom bit is twice as long as the top bit, like this. It doesn't matter, we don't know exactly what these sides look like. But if that's A, B, C, D, there's A, B, and DC. So because they're parallel, there's only one pair of parallel sides there, it's going to be a trapezium. How do I know that these 2 sides here cannot possibly be parallel? Yeah, because they're not the same length as each other. If they were the same length as each other, what would that imply? It's a square, a rectangle, or a rhombus. Okay, it could be square, rectangle, parallelogram, or rhombus. But the fact that the bottom one is twice as long as the top one means it can only be a trapezium. Okay, it can only be a trapezium in that particular case that we've got. So this one, I wonder if I left a bit of space on this one. This one's going to take up a little bit more space, so I would strongly recommend here doing your diagrams and you're working out nice and small for this question, okay? Just because there's a few different things we can do here. So when you're doing your working out for this one, please make this nice and small. Okay, so P, Q, and R are the coordinates, blah, 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 and blah, 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 and blah, blah, blah. Find the coordinates of the point S so that PQRS forms a parallelogram. So, I don't know where these points are. When I'm trying to sketch 3-dimensional coordinates, I literally can't do that, okay? So all you need to do is just take 3 points, P, Q, and R, P, Q, and R, and now we're going to think, where could I put another point that would make a parallelogram? Does anybody want to come up and see where they think they could put one of the points? Up to the where, sorry? So like this kind of one? Yeah. Okay, so this is one of the suggested points that can be. I'm going to call that one S1. like under here, okay? So you could also have it down here. I'm going to call that one S2. Where else? Or it could be over here, okay? Or it could be S3. No, can't do one up there. So we've got actually this set of 3 shapes that it could be, okay? The only things I know for sure is that it says PQRS forms a parallelogram. Now, if it just said that the 4 points form a parallelogram, it could be in any one of these locations. So you have to think about where can it be, bearing in mind it goes PQRS. That's the way it follows. So it definitely goes from P to Q, and it definitely goes from Q to R. Whoops, that's a terrible drawn line. So the only one it can possibly be is S2. Okay, so it has to be this one. Otherwise, this one up here would be PQSR. This one would be PSQR. So it has to be the one that makes the letters make sense. Be careful, because if this question was worded differently, they may ask you to find all 3 coordinates. What could they change about the question that would mean that you have to find all of those coordinates of S1, S2, and S3? Yes, instead of saying PQRS, it could just say, find the coordinates of S so that all 4 points form a parallelogram, so that the coordinates form a parallelogram. This one is interesting because the order of the letters forces us to go with S2 that we have down here. So the sketch is going to be really helpful. Now, this doesn't look like the world's best parallelogram, but obviously these 2 sides are parallel to each other. So if these 2 sides are parallel to each other, if PQ is parallel to this side, we know that PQ must be equal to, I'm just going to call that one S now, must be equal to SR. That's one of the things we know. What other facts can we see from this? Muhi? I mean like another, are there any, yeah, because it's in 3 dimensions. Is there any other kind of statement like this that anybody could tell me is true? Okay, and also PS is equal to QR. Okay, so we're trying to get to S. So if I wanted to get to S, I could find out what QR is, I could go to P, and then I could go and add that on. I'm going to just say that again because it's a little bit confusing. If I want to get to S, I can find out what QR is, knowing that QR is the same as PS. I can get my P coordinate, and I can just add on PS, and it will mean that I'll end up at S2. It's kind of like just having different pathways. If you wanted to, you could take the R coordinate, and you could add on RS, but RS is actually QP. Or you could take the Q coordinate, add on QR, and then add on RS, or add on QP, and then add on PS. It's just about taking different pathways around the shape that you can do. So which one do we actually want to do?
Does it really matter?
No, it doesn't matter. Just tell me one to do.
PQSR.
So we'll go from P to, I'm confused now.
The top one.
We don't want to go from the top one because that's the furthest away from it.
No, you meant the top out of the No, the top out of the 2. As in the PQ. Find out what PQ is. And
Yeah.
then put it in, like, make it equal to, like, have a...
Oh, you mean the top one of this one?
Yeah.
Okay, yeah.
That's what I meant.
I probably would write that as then QP equals RS.
Yeah.
Okay, now we're here.
It's S minus R, yeah.
Okay, so QP is P minus Q, which is 4 minus 9 minus 3. Minus, am I doing this right? Minus 7 minus 7 minus 7. So that's minus 3.
Minus 3, minus 2, and positive 4.
Okay, good. Now, if I want to get to the position S, I might just call it the position S like this, or I could have called it OS to go from the origin to S. Either of those things would be absolutely fine here. I know that if I'm trying to get to S, first of all, I need to get to P, then I need to add on PS.
Wait, so where are we starting from?
Nowhere. The O is origin. The O is this origin down here.
So what are you doing? Why would you do the what? Position vector S and...
That's what I'm trying to get to.
I'm not sure.
If you don't want me to do this OS, I won't do it.
I'm thinking of it another way, that's why.
So the position vector S, you go to P, first of all, the position vector
So
of
let's
P.
start from Q.
No, we're starting from P.
Sir, why don't we just equate that vector that we just worked out, QP,
Yeah.
make it equal to S, which is an unknown, take away the position vector of R.
So you want to do this. You want to say that QP equals, we know that this thing is S minus R.
Yes.
And you know what R is.
Yeah.
Okay, well, let me just show you what happens here. You're going to get that QP plus R equals
Oh, is that what you're doing?
S. Yeah.
Okay, that's all I was getting confused by, because you kept saying P, and I don't know where P's come from.
Yeah, and actually I don't know why I'm at P, because
We're at R.
we should be at R. So that shouldn't be a P, that should be an R.
That's what I was saying.
So it's R
Plus QP.
plus QP. And then we're going to go through this all again, because you've probably got yourself confused, because Rayhan and I have been arguing. So you get 8 minus 2, 0, plus minus 3 minus 2, 4.
So it's 5.
5 minus 4, 4.
Yeah.
So S is 5 minus 4,
There we go.
4. There are two ways of doing this, okay? All we did here, it was just the confusion of some of the letters.
No, it's not R minus it.
Yeah.
QP.
Yeah, this is going to be there.
From R to S. So we have to do it in that order.
I haven't taught anything wrong here. The only thing I did wrong was I put the letter, I wrote this letter down wrong.
Yeah, it's that statement there rearranged, and then all we did was just sub in the value.
So this is, I think there's two ways of looking at it. One of them is just like, oh, QP is the same as RS. We can work out what QP is, and we know that RS is S minus R. We know what R is, so we can rearrange it. This has some meaning as well, though. This is saying, go to the R coordinate and add on the pathway QP. Well, here's the R coordinate. If you add on the pathway QP, you end up at S. So this way that I was doing over here is pathways. This way that Rayhan was doing it over here was just knowing that if these are equal, he can use the statement that RS is S minus R. It's just that Rayhan was talking about one thing, I was talking about something else, and I didn't know that you were talking about something else. And I decided to write that as P rather than as R. So there was a double layer of mad confusion there.
That's why we did that one time in third maths as well.
Yeah. Okay. Main thing is you're probably going to do a question in this exercise where it's going to be all three positions. So you just need to move it around. If you wanted to get up to this one up here, it would obviously be P plus RQ. RQ is that direction, so you can just use that to kind of add on to it. Right, let's just do the next question, shall we? Yeah. Okay, the next question is introducing scalars and comparing coefficients. Now, this is something you've done in Year 12. I have stolen this example from the Year 12 lesson that I am teaching on Thursday, and we're going to do it again so that we can just do the exact same thing, but in 3 dimensions, okay? So that's the only difference. I'm about to do one in 2D, then we're going to do it in 3D.
So can I have a question?
Yep. Take this one. Whose is that?
No idea. I ended up with.
Okay. So we're going to introduce this topic. It says introducing scalars and comparing coefficients. Remember when we had identities like this kind of thing here. ax squared plus 3x equals 2x squared plus bx. You're going to be like, huh, why is he talking about algebra? But it's because we're going to be using it in this topic. We could compare the coefficients. We also did this in partial fractions as well. So we can clearly see that a is 2 and that b is 3. And you can do the exact same thing with non-parallel vectors. You can compare the components of those vectors that would make things true, okay? Right. Let's read the question first of all to see what's happening here. It says OACB, notice how it goes OACB around the outside, is a parallelogram where OA is A and OB is B. Prove that the diagonals bisect each other. Okay, we're going to try and prove that this diagonal here and this diagonal here, that first of all that they intersect each other. Well, we can see that they intersect each other, but in 3 dimensions it's not always as obvious if 2 lines are going to intersect each other. The other thing that it wants us to prove, not only that they cross each other, what does bisect mean? Directly in the middle. It's going to be exactly in half, okay? And the strategy that we use this is we try and find out the vector OX in two different ways and then compare the coefficients. We're going to do the same thing in 3D in a second. So everything I'm doing here, I want you to think about how that's going to then relate to what we do in the next part, okay? Before we get started, I've written down these two words here, lambda and mu. Have we seen those letters before? Yeah. Okay, so lambda is the Greek letter that looks like this, and mu is a Greek letter that looks like a tail to begin with. You go up, and then you draw the letter U, okay? Those are just two constants that I'm going to use here. Right, so we're going to try and get to OX in two different ways. Way number 1. Describing pathways using this kind of notation. Can somebody tell me how you could arrive at X? Ronak, could you tell me how you could arrive at X, describing it using like OA pathways? We don't know that. We're trying to prove that it goes there. We can't go there by saying it's half of O to C. We don't know that. We just don't know that it's a half. We know that it's something to do with O to C. So I'm going to go with your original suggestion, but I won't put a half in front of it. We're going to say that it is lambda OC. Okay? It is some fraction of OC. So here, lambda is a fraction, and we know that lambda is between 0 and 1. I know it's pretty obvious that lambda is going to be 2 because we're trying to prove that, but we don't know that that's where X is. We don't know that that's actually it. So we're hoping at the end that lambda, when we compare the coefficients, we hope it's going to be a half. Let's not do way 2 yet, sorry guys. But what is OC? Good. It is A plus B. OC, to go from here to here, is A plus B. So that gives us lambda A plus lambda B. That's way number 1. What is way number 2 of getting from O to X? I need to go in a different pathway. Tell me what your pathways are. You want me to go from O to B?
The one that we did was OAC.
We didn't do that. We just did this pathway for the first one. Okay. What's? Yeah, we're going to do OB plus BX. Okay. Now OB is just B. Now BX is some fraction along the line of BA. Yeah? This time, mu is a fraction, and mu is between 0 and 1. We know what the value of mu is, though. What is the value of mu going to be? It's going to be a half. Otherwise, geometry doesn't work. Okay? So we know that the answer is that lambda is a half and that mu is a half. But this word prove doesn't mean you can use that. It means you have to, at the end, show that it is a half. So we've got mu BA. Well, what is BA? Yeah, it's minus B plus A. Or A minus B, whichever way you wanted to think about that. So that gives us mu A. And then how many lots of B do I have? I have mu B and regular B. So it's 1 minus mu, lots of B. You've got 1 minus mu. Okay? So we have now got to an interesting point. I can tell you're all fascinated by this. We have now got OX is lambda A, but down here we've got that OX is mu A. Yeah, it does. Great. So lambda equals mu. And that is by comparing the A coefficient. We've proved that lambda must be equal to mu. We're then going to prove, or not prove, we're then going to compare the B coefficient. Lambda B is 1 minus mu b. Which means that when we compare the b coefficient, we get that lambda is equal to 1 minus mu. So we can sub one of them in. Why don't I substitute that one as mu? Doesn't really matter. So I get mu equals 1 minus mu. 2 mu is 1. So mu is equal to a half, which we know is equal to lambda, because mu and lambda are the same as each other. So the diagonals bisect. Okay, the diagonals bisect each other. This is pure year 1.
We didn't learn in period 1.
You didn't learn this in pure year 1.
I think we did.
You should have done.
Well, I was learning.
So that's showing off. We didn't learn this in pure year 1, but I did it myself. Did everyone spot why it was 1 minus mu down here? Because I did it a bit quick. Yeah, it's just the same thing, this bit expanded and then factorized, so it looks like this. This is a really neat trick for showing a proof of something with vectors, okay? We're about to do the same thing. Oh, actually, I think I'm going to give you one to have a go at, aren't I? Okay, so it's your turn on the next page. This time it is not so nice. I'm not telling you how it's going to compare, but you're going to try and do something that's a little bit different. We will go through it in just a moment though, okay? So I'm going to stop recording there.